that work, now that we have more of a sense of which sorts of star-forming galaxies are responsible for cosmic reionization, we want to know what went into those galaxies that made them special to become Lyman continuum emitters. And so I've stacked 89 spectra 120 different ways, and we was able to produce spectra that look like this. And with the stacking, we get these beautiful features that pop out, these wind lines here, the O6 and N5, and these tell us something about the very young stellar populations, and then we get these photospheric lines to like carbon-3 that tell us something about the older stellar populations. And by older, I mean things that are like 4 to 10 million years. And so with this, we can actually then start to understand something about the feedback mechanisms that are involved with shaping the interstellar medium. And so the very young stellar populations that these wind lines tell us about, those are related to ionizing feedback. So the Lyman continuum itself is able to basically brute force its way out of the interstellar medium. Then for sort of middle-aged stellar populations, we've got Wolf-Rayet stars, and they're involved with stellar winds and some ionization. And then your older stellar populations have had the chance for supernovae to go off and start to literally like punch holes in the interstellar medium. And so we can measure these light fractions, these contributions of these populations to the SED, and do this for all of these stacks and get a sense of what's actually going on in a statistical way. And so when we compare sort of the relative contribution of these old mechanical feedback dominated components versus these very young stellar populations, we get this two-stage burst picture that is optimal for Lyman continuum escape. So in the first stage, your supernovae go off and they punch these holes in the interstellar medium. And then you follow up with a young burst that then produces these ionizing photons that brute force their way through what's left. And if you have any questions about about any of this or any of the geometry that's related to the interstellar medium, come see my poster.
Yeah, so hey everyone, my name is Will, and I'm a grad student at the University of Michigan working with Professor Sean Johnson, who is also here. So my research is on giant quasar nebula. So by giant quasar nebula, which is basically CGM gas, CGM scale gas around quasars, because we need a quasar to photoionize the gas around it, making them emit in recombination and collisional excited line, such as H beta, O2, and O3. So here is an example, which is HT0238, a radio quiet quasar at a redshift of 0.6, and living in a rich environment because we want to figure out where the gas is coming from a redshifting survey. And after quasar and continuum subtraction, we are able to detect a 70 kiloparsec scale nebula around it. And from the kinematic and morphology, we think the nebula arises from tidal and ram pressure stripping. And from the O2 3729 doublet ratio, we are able to measure electron number density shown right here. And from the photoionization simulation with cloudy and different ionization state lines, we are able to derive another density, but those two densities don't really agree. And we think the discrepancy is caused by quasar variability on a really long time scale, 10 to the 4 to 10 to the 5. 5 years. So if you are interested, come talk to me. My poster is right there. You should remember what I look like right now. Yeah, thanks.
Hello, everyone. My name is Greco Yarsun. I am a postdoc at Johns Hopkins, and today I'm going to tell you about how we are using observations of redshift 2 to constrain the baryon cycle around cosmic noon. So the key point here is that to probe H1 gas at these redshifts, we turn to damped Lyman alpha absorbers, or DLAs, which correspond to the highest column density H1 gas clouds that we can probe in the spectral background sources, mostly quasars. And in particular, what we did was we took a sample of 14 DLAs that were particularly metal rich. And what we did was to point KCWI as integral field spectrograph toward each one of these 14 DLAs to observe something like what we see here, where at the center of the field of view, we have the DLA, and with integral field spectroscopy, we can identify any galaxies that emit in Lyman alpha. that could be associated with the damp Lyman alpha absorber. And in particular, for this system, we found 2 Lyman alpha meters, one over here and another one over there, at impact parameters between 50 and 70 kiloparsecs. And in addition, we also know that in this system, there's a massive CO-emitting galaxy at a closer impact parameter of about 15 kiloparsecs. So apart from those 2 Lyman alpha meters, we detected 4 more Lyman alpha emitting galaxies, meaning that we detected a total of 6 in the sample of 14. And the most interesting feature of these detections or non-detections is that if you look at the highest metallicity of the H1 gas, so to the right on the x-axis, this is Lyman alpha luminosity on the y-axis, we do not detect any Lyman alpha meters at the highest metallicities of the H1 gas, which leads to the main takeaway of this work that it appears that the galaxies associated with the most metal-rich, highest column density H1 gas clouds at redshift 2 are faint in Lyman alpha, likely indicating that these galaxies are massive, heavily star-forming, and very dusty. So if you're interested in this or you want to talk more, please come find me. Thank you.
Oops. Wait, how do I go back? Okay. Hi, everyone. I'm Diane, a PhD candidate at Rutgers University, and I'm really impressed by all the analytic and numerical studies to parameterize star formation that's been presented in this conference. But what if the data could actually tell you that itself? That would be really interesting, right? So we're coming up with a machine learning approach to input some pixel scale properties from the FIRE2 simulations and output equations for the surface density of star formation rate using an algorithm called symbolic regression. And we use a baseline model, which is a random forest decision tree called XGBoost, which also inputs the features and outputs a target output, but it is not interpretable. So we're doing the same thing, but hopefully getting out interpretable equations out of it. But does this method actually really work? It sounds great, but so what we're finding is that this method is capturing the mean of the star formation rate surface densities quite well, but doesn't necessarily replicate the physical dispersion in, say, the Kennicutt-Schmidt plane particularly well. So if you're interested in some of the more technical details of this project, please come visit me at my poster in my little corner there next to the model, number 37. Thank you.
Hi, it's me again. I'm Alison, and I'm based in Vancouver in Canada, and I'm still interested in AGN feedback. And yeah, so in this project, we're interested to learn how AGN feedback affects the gas supply for star formation. And again, another case study, but this one is at cosmic noon, but this one is still a very massive galaxy of stellar mass of 10 to the 11.6, and it's forming stars at a spectacular star formation rate of more than 1,000. So by any means, this is well, extreme galaxy, and of course it is also radio loud, type 2 AGN. What we've done here is that we have obtained very deep and high resolution ARMA data with band 6 on top and band 4, which is at the bottom. So the grayscale image you're seeing is the continuum image, and well, within the red ellipse, you see that is the host galaxy. So you see it's brighter in band 6 that is dominated by dust emission. And this smaller blob to the left here, it is one of the radio lobes. So that is synchrotron emission, which explains why it's brighter in band 4. But what is really new about this work is that we got 4 lines, or we got both of the atomic carbon transitions, and intensity maps are shown in the blue contours. And we also got CO 7 to 6 and 4 to 3. And you see that all these 4 lines, they have quite different geometry. And in particular, I highlight a molecular gas tail that is dust-free. And it is not super obvious here, but when you look at C1 1 to 0, you will see that it has two peaks and it's not peaking in the center of the host galaxy. So we are still very much working on understanding what this all means in terms of the molecular gas excitation. I believe we have a lot of information that we can tease out by modeling the line excitation spectral by spectral. And we have also been inferring systematic uncertainty in molecular gas mass calibration, because atomic carbon and CO, they are two different independent molecular gas tracer. And so there's also another work led by another student where we're modeling the kinematics of this molecular gas, and we find that there's a substantial misalignment between ionized and molecular gas phase. And paradoxically, we find that the dynamical mass is smaller than the known barrier mass. And if you want to find out more, then you can look at the smallest poster that is over there. And yeah, thanks.
Let's thank all the speakers of this session. And now it's time for a coffee break, which will be 10 minutes longer, you say? Yeah. See you back at 3:40? Yeah. Thanks.